Welcome back to the Black Belt track. Today we're going to have talks that are going to be even more amazing than yesterday, if that's only possible. And yes, it will be possible, and I count on you to rate those talks in the mobile app and say how awesome and fantastic and everything they are. Again, my advice is if you don't like the talks, don't rate them. That's maybe survivorship bias or something like that, I don't know. So for the first talk this morning, we want to talk about security. We don't care about security, said no company ever. Everybody will tell you we care about security, it's super important, but then it really matters in how do you care about security. And there is an approach, which is the ostrich approach, when you're like, there are no bugs in our products, and if you see bugs, we are going to sue you. There is another approach, which is we know that software is made by humans, and humans are pretty bad at writing software, but unfortunately, so far, they are the only people who can do it. So that's why we have humans to write software. So software has bugs, and sometimes security bugs. So what matters is how you address them. So to talk about that, there is Michael Crosby, who is a long-time maintainer of Docker, who then went over to write libcontainer, and then run C, and then containerd. So that we took like the most qualified person to talk about this. And I also have something special with Mike. He's the one who carried over the last contribution I made to Docker. Sometimes it's hard to contribute to Docker, especially when you contribute something complicated. The last time I contributed to Docker was 3 years ago, I think, and it was the dash privilege flag. And after a few back and forth with Mike, it basically, I don't know if he used those words, I don't remember. It was basically like, Jerome, go back to do talks and stuff. I'm going to take your shitty code and make it nice, and then we will merge it. But then it means we have privileged containers, which is a pretty big security issue anyway. But anyway. Ladies and gentlemen, Mike Crosby.
All right, thanks. So yeah, the title of my talk is Securing Containers One Patch at a Time. And it's a pretty small agenda that we'll go over today, but basically we'll do some preface with like what are CVEs and to get everyone up to speed, like are CVEs good? Kind of a little history on CVE we had in the past, like 3 years ago. And then we'll finally look at a CVE that we did in December of 2016, which I thought was pretty interesting and wanted to share with everyone. And then if we have time at the end, we can do some Q&A. So kind of like Jerome already introduced, I can skip this. But we can just jump right in and kind of define like what a CVE is, and it basically stands for Common Vulnerabilities and Exposures. And overall, it's just a database of exposures for software, services, things like that. And it has a pretty decent naming schema where the first 3 letters are CVE, and then you have the date, the year that the CVE was found and reported, and then kind of the a 4-digit unique ID for each CVE of that year. And you can see all these CVEs at this URL, and it's pretty easy to search through the database, find what versions of software were affected, and so on. So like a big question is always, are CVEs bad? Like if a software project has 10 CVEs, is it less secure than a software project that has none? And the short answer is no, CVEs are good. And CVEs are part of the security process that makes software secure. Like, there's only a few reasons for a project not to have CVEs. Either no one's using it, or no one cares enough to try to pop it. And so with containers, we've seen like a large user base. So even at the runtime level, over the past 3-4 years, we actually have had less than probably 5 to 10 CVEs on the runtime. But every one of them is very valuable to making the entire platform stronger as we go. So we kind of have a CVE process that we follow. This is kind of a summary. I see a lot of the security team here, so they can point out all my flaws. But what happens usually is we receive the report, and this usually happens on a private mailing list. So we have a security@docker.com, and in OCI for the Run C project, we have a maintainers mailing list where we can receive these kind of sensitive emails upon vulnerabilities or questions, things like that. So secondly, like after we receive an email, we need to verify it. And one of the things that I really like about the security industry is when they do send an email with a vulnerability, like they have very good reproduction steps. They come with scripts, maybe C programs if you're dropping down to the syscall level to break out of a container. So it's really easy on the verification part of it. And then finally, after we verified it, we kind of look for a severity of it. We work on a fix for the vulnerability. And then after that, sometime during this time, we'll issue a new CVE that gets our number where we can all work around and have kind of this ID to base the fix and vulnerability on. After that, after we have a fix, we have a CVE, we go ahead and send to downstreams. So this includes distros, large clouds, big users, select group of users that extensively use the project. And they help verifying it. And at this time, it starts kind of a 1 to 2 week embargo period where it gives distros time to apply the patch to the tree, make packages, so that after this embargo period ends and we release publicly, you have packages ready to be downloaded and fixed as the vulnerability is made public. So overall, security is more of a process. It's not a sprint. You can't just take a backlog and spend 2 weeks sprinting on it to make your software secure. It's something that happens over years, and we've been working on container runtimes for almost 4 years now. And there's new security features that we add, there's different vulnerabilities that come out that we fix, and it's just an ongoing process. So the first kind of vulnerability is something from almost 3 years ago, and it had to do with proc kernel hot plug. And this was before Run C and even before libcontainer. So to set the stage, it was 2 weeks before the Docker 0.7 release. We were introducing libcontainer at the time. And before that, we used LXC. And with this update, we were switching the default from LXC to libcontainer, and like going from there where we're developing features on the runtime side and finishing things with Docker. And so 2 weeks before that, we sent out an RC, and then a user named iBuildTheCloud. If you know him, he's Darren from Rancher. He sent us an email and said, hey, I found a way to execute a script on the host as root. And so like being 2 weeks before releasing like our initial runtime, this isn't really the thing that I wanted to see at the time, but it was very interesting nonetheless. So I'll kind of show you or explain this vulnerability. I won't show it on my system because I still have to finish this talk and I don't want to wreck things. But at the time, Docker only used AUFS, and it basically only ran on Ubuntu. So the first part of the vulnerability was guessing the root of the container on the host file system, and this was pretty simple because you didn't have a varlib docker overlay, varlib docker AUFS. It was just varlib docker containers. So this part was simple to guess. And after you guessed kind of the root of where all containers live, you needed to get the ID of the container. And you could do this from inside the container by catting out proc1 C group, because C groups are created with the ID of the container as the directory within the hierarchy. And so after you get that ID, you can append that to the root that you guessed. And then the next step was, while you're in the container, you write a script to your root directory. You could do things like just echo out something or worse. And then finally pulling it all together, you just echo this path in the proc kernel hot plug, and it would execute on the host as root. And it was basically because the host would just take that path, it would see, hey, this is a valid path for me, all right, I'll run it. And that was the vulnerability. And so at the time, what it really was just a missing AppArmor profile that we didn't have in the RC. So we ended up adding that this vulnerability was fixed, but also we ended up introducing something called mass paths and read-only paths. So our kind of process from the beginning was you should always be using an LSM like AppArmor or SE Linux, but even if you don't, and there's no reason for you not to, but even if you don't, we'll try our best to make containers as secure as possible. So with mass paths and read-only paths within runc and libcontainer, we mask out things like proc sys and proc IRQ, things like that. So it was kind of a rough time 2 weeks before release of this, but at least I can have a slide today to say that security was our #1 focus since day one of libcontainer. So now onto the CVE in December. This is the one that was really interesting to me. And it was basically using Ptrace to access privileged process FDs. And I'll expand on this in a minute. But before we do that, we kind of need to understand like how containers are created and what the execution flow for it is. So containers always have two processes. They have a parent process that lives in the host, and it forks off a child process that gets placed inside the container, or it becomes the container. And with this, during the initial creation of the container, we have an init process, and this init process is part of runc today. So you have the runc command line, you say runc create or runc run. It forks off an init process that it owns. It gets cloned into new namespaces, or it creates namespaces. And then after it's in new namespaces for the container, it starts to set up the root file system. And so that consists of mounting proc, dev, sys. It will do all your bind mounts for volumes and things like that. And then after the root file system is set up, we start applying LSMs and dropping capabilities until the final exec. So AppArmor SE Linux are applied, capabilities are dropped, we change the user if asked, and then there's a FIFO that we block on to implement the runc create start split so that things like hooks aren't needed anymore. And then finally, after you call like runc start, this FIFO unblocks and the exec of your final user's process is called, so your MySQL, Redis, or Bash runs at that time, and the libcontainer init process no longer exists. It becomes your containers process. And so the execution flow for additional processes like Docker exec is the same way, only the first part is instead of creating new namespaces, we join existing namespaces. And then the flow's the same. We apply the same AppArmor profiles, we drop cabs, change user, and exec, only we don't have the synchronization FIFO here. So this all stemmed from a LXC CVE that they had. And basically their CVE was a process that is joining container can be Ptraced by another process already inside the container. And LXC was basically using the same model as us, only they were passing the host proc as an FD to their container process so that they could set LSMs that way. And this was initially reported by Cypher on our OCI mailing list saying, hey, I've seen this LXC CVE. We need to see if runc is vulnerable to attack like this. So this kind of started our CVE process for runc. We needed to do a few things such as like just double check, is runc affected? What's the severity of this? Is it a privileged escalation? Is it a container breakout? What are some proposed fixes that we can make? And are there any additional ways to use this attack vector that you could break out of a container? And so the answer to the first question was pretty simple, because we've seen in the slide before, we do have this FIFO that we passed, which is passed as an FD for synchronization. And this FIFO, this FD is actually the directory FD to the runc state directory so that the init process can find the FIFO within that. So we're affected. It was pretty obvious. We really didn't have to double check anything or try to exploit. We kind of know like, yeah, this affects us as well. So I'll kind of demo this vulnerability. I have a old runc built right here, so it's in my root directory. I'm not using the one installed on my host. And in this first terminal, this will be our kind of attack process. So it will be the initial container process that will try to walk out of the FD when I add an additional process in the second terminal window. So if I run runc run test, just naming this container test, we will drop into a container here. We can PS this and see that we're in the container. We have a PID1. So in my second terminal, I'll add an exec, and this is where the initial process running inside the container, it's some untrusted thing, tries to exploit the time it takes between a process joining the container's namespaces and it finally getting all the capabilities dropped before the exec. And in this demo, I added a sleep in before the exec so I could like demo this on stage because it's too fast to demo normally. So if I do runc exec test and then just do ls, we'll see ls blocks for like 30 seconds while I do this. So I'll run that, and in my original terminal, I'll find the process. And you can see that there's a self-exe process there, and that's the runc init process that's setting things up. So if I just ls proc 12 fd, and then it's on 4, and we have container dir, state dir, and then root. I have a file there called host root. That's the root of my host system. And so like the simplest way to exploit this is you just ls and walk out. And like when the exec process runs, it's just lsing in the container. So you see container root. So that's like, it's like super trivial how this worked. So after that, we knew runc was affected, so we needed to look at severity. And so there's different things that affect this. Because of the LXC CVE, we knew it had to do with Ptrace. So we asked questions like, does capsys Ptrace affect this? Because this is something that we automatically drop in Docker by default. So no containers run with this. And secondly, does LSMs like AppArmor or SC Linux protect against this? Because it helps judge how affected people are, our users, and things like that. And then finally, like looking at different kernel versions and such, is it fixed in a newer kernel, is it kernel dependent, and so on. So for the first question, does capsys Ptrace block this? And the basic answer was no. It didn't matter whether you had capsys Ptrace or not, you could still walk out of the FD. And then for AppArmor and SC Linux, the answer was more fuzzy. It seemed to depend on kernel version and AppArmor version. So we tested on like Ubuntu and Debian. Ubuntu I wasn't able to exploit on my machine with AppArmor, but on Debian it allowed it. SC Linux, it would allow you to walk out, but you couldn't read all host files. But there were some files depending on how they were labeled, like etc password and etc shadow, that you could read, and so on. So the answers were kind of, and that's really not a good answer when it comes to security. So finally, whether it's kernel dependent, was it fixed in a new kernel, and we've seen various issues with different kernel versions or distros, but nothing was really conclusive. So basically, from what we could tell, it was all affected. There wasn't really a good way to mitigate this from what we had today. So we looked at a few proposed fixes, and the first one was we only use this FIFO on the initial container creation for synchronization, so we can just remove it from exec and be done with it. But that never answered the question of what else can use this attack vector. So we have another person on our team at Docker, and he's kind of like the Bane to my Batman. I try to build a nice Gotham and he just tears it down. But in all seriously, like he's the first person I go to whenever I'm working on something like this because he's so good at these type of things. And if you've ever looked in libcontainer and looked at mounting code for bind mounts and how we handle symlinks, and all that code is because of him, of finding ways to break out when mounting things on top of symlinks and how the kernel resolves the symlinks on mounts. So whenever I have any questions, I kind of do like the bad co-worker does. I walk over to his desk and be like, hey, you got a minute? And show him this vulnerability, kind of show him some proposed fixes we were thinking about. And within a few days, we get an email saying like, hey, I found an additional way to exploit this without like just simply walking out. And here's an extra vulnerability with proc exe. And so at the time, it's like, oh, perfect. It's kind of what we wanted, but not what I wanted to hear. So we can look at this additional vulnerability where we went from one vulnerability, which was pretty tricky when dealing with Ptrace, to 2 now. And so with proc exe, this is a crazy file. And basically, for each process, it's a file that points to the binary that's being executed. Only, I don't know how to classify this, whether it's a symlink, a pointer, but it's basically a symlink on steroids that can break out of pivot roots, CH roots. It doesn't matter. It can always find its way home. And kind of a simple way of exploiting this was you could just echo into it and rewrite the run C init process or binary on the host. So you could echo just a simple like echo hi, so the next time you run C, it'll be like hi, and not even execute your container. Or you can do worse things, like the next time you run C, it does evil things because you replaced it with a bash script from inside the container. So the actual breakout is a lot more complex than this. This is kind of like an approximation. There were issues when you go to try to write to it, it'll say text file busy, but because of the exec, when it goes from the run init process to the containers process, you grab a hold of the FD while it's the run init, wait for it to exec over to your MySQL or whatever, and then you open it up and write it. And it still finds its way home. And like it's an amazing file. So kind of back to the drawing board, why is this all happening? Like, we dropped capsys ptrace. Like, why are processes still being able to trace other processes in the container? And we know Docker drops it by default. And the basic reasoning is because we're attacking from an existing process, and that existing process was the PID1, it's the parent of all processes within the container. So the parent can always ptrace its children. So as we're looking at different fixes and so on, one of the things that came to mind was this dumpable setting, because like who can forget a name like dumpable? But this is the description from the man page for dumpable, and it basically has nothing to do with like somewhat what it does. It's pretty confusing, but if you've read man pages for kernel stuff, you know the pain. And so basically, I was researching this dumpable setting. I wanted to know like how it interacts with other things like capsys ptrace. And so I was looking for some rules for like when can you ptrace processes. And basically there's no man pages for this stuff. Dumpable has this small section with a really abstract explanation of it. It just defines some functionality of when it's reset, when it's applied. There's not much on Google for this stuff of like when a process can be ptraced. So basically you're left to reading kernel source code and figuring out like what are the if blocks for can this process be ptraced by this other process. And so for simplicity, I kind of compiled this simple list of you can ptrace another process if you are the parent and it is dumpable. There's kind of like and an or in the kernel, or you have capsys ptrace. So with the capability, you can ptrace anything, parent or not. If you don't have it, you can ptrace if you're a parent and the process that you want to trace is dumpable. If it's not dumpable, then you can't. So the idea for the proposed fix was like, what if we change the dumpable setting only for the run init process? say while the container is being set up, while initial processes are being added to the container, just don't allow this thing to be dumpable. And from the man pages, you learn that dumpable is reset on exec, so that's perfect. That allows us to keep our init process, this privileged process, as a non-dumpable process during initialization. And then when we exec over to the containers process, it gets reset automatically, and different things, you'll be able to run debuggers, strace, and things within the container like you would normally do. And the only side effect for this is that you cannot strace run C. But if you've ever tried to strace Go programs that fork a lot, you can tell that this isn't really helpful anyway, because it's all over the place with as many threads and things as it forks off. So it was a compromise we were willing to make. So we ended up implementing these 3 lines as a fix. So this went into our initial init code. After we fork off the process, this is the first thing that gets set when we clone into the init process. So immediately set this as non-dumpable and then go along our way of setting up the container. So, did it work? And it was very effective. So it stopped the walking of the FD, it stopped the overriding of the exe file. Sorry. But whenever we have a fix, we like to do some stress testing. So we'll execute 10,000 containers or so over a couple of days. And from the initial vulnerability, we were able to exploit it 100 out of 100 times. And after this Ptrace fix, we're able to exploit it 3 out of 100 times. And for some people, this may look like progress, but for most of us in this room, we all know that this is pretty much the furthest thing from progress. It means we have a race, and it's basically one of the worst things that can happen. So, especially when you're at this level of the stack where you're interfacing with syscalls and execing new processes, when you have a race, it's not fun. So now we went from 1 vulnerability to 2 vulnerabilities in a race. So we've got to figure out where this is racing. And basically we know a few facts. We know that the FD can only be accessed whenever the process is dumpable. We know that FD cannot be accessed after it's closed. And we know that dumpable is reset on exec. And there's one more data point, that all these FDs have O_close_exec set. And if you don't know about O_close_exec or close-on-exec, it's a flag that's set on FDs when you open, or you can use an FNCTL to set this. And it makes all the FDs set with this flag be closed the next time the application execs. And so there's a lot of hard questions in life, and there's some questions that I've never asked, such as how does water get in a water tower? And there's other questions that I've never asked, such as when is close_exec FDs actually closed? And it's not no one's ever asked me this. I've never even thought about asking such a question, but when you're faced with races at this level, it's kind of like some of the dark secrets of the Linux kernel that you have to dig into. So it was basically one of the ideas we had, maybe close_exec on this FD, and when dumpable is being reset isn't atomic. And I think for a lot of people, every time you use something lower in the stack, whatever's lower in the stack is magic. We think oh, I make this syscall and it's atomic. And really, container runtime, Docker, run C, the kernel, it's all written by people like you and me, and it's all function calls. And so when you call execve in the kernel, it's a function just like anything else, and it calls multiple other functions. And for our purpose here, what's happening is the set dumpable on the current task is being reset before the close_exec on all the FDs are firing. So if you can imagine what type of race this is in a syscall, from a difference of 10, 15 lines to being able to race and exploit this to break out of a container. It's pretty crazy that something like this happens. Like it's within milliseconds or less. So if we look at kind of the exec flow within the kernel, what happens is the new binary that you pass on the path to exec, it gets loaded, and at that time, this super symlink exe pointer thingy gets reset to the new binary. So there was no race in this part of the exploit. It gets reset after the new binary is loaded. And then it would go down, change the dumpable setting, reset it to default, allowing the process to be dumpable. Close to the very end, all the close execs would fire and close all these FDs, and then the new code is executed. And you can kind of look at the exec.c code in the kernel to see this more in depth. So finally, on the home stretch for this vulnerability, the final patch was setting the dumpable setting for our init processes and just manually closing these FDs before calling exec. And this allowed us to ensure that the FDs were closed, they couldn't be accessed, and we're not depending on the ordering of when dumpable is reset and when close-on-exec FDs are fired. And so we answered a hard question earlier about when close-on-execs are actually closed, and that slide is false. So Cypher, another maintainer on runC, we went ahead and submitted a kernel patch reordering when close execs happen during the exec process and making sure that they're closed much further up the execution pipe before the dumpable settings and other privilege settings are reset on the process and before its context change. So you can see this commit in the mainline kernel tree. It was issued in, I think it was released in 4.10, but it was also backported all the way back to 3.16. So you don't have to manually close FDs if you're depending on close exec and dumpable. We went ahead and fixed this in the kernel for everyone. So that's kind of my talk on securing containers and a little bit about some CVEs that I found interesting and that I'd share with everyone.
So if you have questions, you can raise your hand and I'm gonna give you the mic so you can ask the question to the other mic.
Thanks. Great talk. So I'm just a little hazy on when all the forking and execing happens. Can you explain why there's not another race between the time the process is forked and you actually take away the dumpable flag? Because that's the first race I was thinking of.
Yeah, so when the parent process forks off, especially in the exec execution flow, it forks off our init process, and then you have to do a set and S call on all the namespace FDs for the main container process that you want to join. So we just set the dumpable flag first and then do all the set and S calls that actually join that process to the container. So initially the first process, that exec process that gets forked off, it's like any other process on the system. And then afterwards it's manually applied to the container and placed inside. So that prevents that race.
Hi, thanks for the great talk. I'm by no means any kind of security expert, but I'm kind of curious how many of these vulnerabilities are more exacerbated by people running as root aside from a secondary user? Like would they have access to proc still, or issues like this are more common maybe?
Yeah, the majority of them. Like, I always hear a lot of people talk about user namespaces and things like that, like it's the savior to containers. But from day one, if you don't want root running in a container, don't run as root. Like that was the simplest thing. And all these vulnerabilities that I shown were because the process was running as root. If you're running as a non-root user, this is something that you don't have to worry about. And like, if you think about containers versus non-contained processes, like non-root in a container is immensely more secure than a non-root process on a system. So yeah, I always recommend non-root users. Like outside of your build pipeline of installing packages and on production, run as non-root.
Thank you.
Other questions? Going once, twice. Okay, thanks again, Mike.